So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Good afternoon, everyone. So welcome to CSE141 again. And today we are continuing our discussion on the instruction set architecture. And being honest, I want to say that the instruction set architecture, I know a lot of you will feel like feel bored yesterday. And well, being honest to you guys, I do feel the same. And you know, like programming in assembly language is never fun. So what I really want to tell you, it's almost the end. So today we are going to finish off the instruction set architecture part really quick. And we are starting a new chapter called performance, which is more interesting and more relevant to the agenda of this class, which I think. But before we start, I still want to bring you back to the very, very big idea behind modern computers that is von Neumann architecture. And remember what? In von Neumann architecture, we have processor and memory, and we have the storage device for persistent storage. And as long as you compile the program, it goes into the persistent storage. Whenever you need to execute a program, we dynamically load the data and instructions associated with that program into your main memory. And the responsibility of the processor is to look through the instruction that we are currently executing and see what the instruction wants us to do. If the instruction wants us to access the data, then we access the data. And if we are done, we just move to the next instruction in a program. Or if the program asks us to jump somewhere, then that's what we should do. And the fancy thing about this architecture is that by loading different programs into memory, your computer can perform completely different tasks. So you don't have to reconfigure the computer. However, the thing is that there are tons of different memory devices. There are different processors. How we can write program easily on von Neumann machine. So it turns out that architects, we invent abstractions called instruction set architecture, which is the contract between hardware and software. It's an abstraction of the underlying architecture, or say underlying von Neumann machine. So it contains the processor abstraction and the memory abstraction. And for the processor abstraction, it defines a set of operations. And for memory abstraction, it defines how big the memory this processor can access. So programs are now the combinations of this instruction. So this is what you know about assembly language. And but the good thing about the abstraction is that when we write programs, no matter you are using high-level language or assembly language, you just don't need to worry about the hardware circuit. So you don't need to. So everything about CSE140 you can forget because the instruction set architecture exists. And so that's a good thing about instruction set architecture. So graphically, this is what I thought about abstraction. So no matter you are using an Intel processor or AMD processor, all you need to know is an x86 processor, and both of them should support exactly the same abstraction as defined by the instruction set architecture. Except for x86 too, x86, there are other processors supporting other instruction set architectures. So for example, like ARM is by far the most popular architecture, and many companies produce processors using ARM instruction set architecture. However, ARM itself is a separate company that only defines the architecture and defines the standard of the sample design that supports this instruction set architecture. And in addition to ARM, many startup companies are thinking about the license fee from ARM is too expensive. So that's why we have another camp of instruction set architecture nowadays called RISC-V. And the authors of RISC-V is actually John Hennessy and David Patterson. So, so you can consider RISC-V as the 5th generation of MIPS, which is the one that we use in the textbook. And for the MIPS, previously they have the implementation successfully coming into the famous game console like PlayStation and PlayStation 2 using by Sony. Okay, so that's so if you remember the previous graph, so it's not too hard to tell that there are many models of processors support one instruction set architecture, but not each processor manufacturer has their own instruction set architecture, and we haven't seen a processor support multiple instruction set architectures in hardware for a while, and we have not seen an instruction set architecture that is only unique to one model of the processor as well. And although nobody is right now really well, there are still people using MIPS, but there are not a lot. So, but this is the simplest kind of instruction set architecture that later on inspires RISC-V and ARM. So that's why we start with the MIPS in this textbook. And the basic idea of MIPS is that it's a byte addressing memory abstraction with 2 to the 32 bytes total memory addresses available, ranging from 0 to 2 to the 32 minus 1. And in terms of processor operations, we support 50 different operations. They would perform arithmetic logic operations. They would help us to change your program counter whenever it's necessary. They would help us to load data, store data from or to your memory and put them in the registers. And regarding registers, we have 32 32-bit registers. And each of the MIPS instructions is 32-bit wide. So there are many 32 in MIPS instruction set architecture, 32-bit registers, 32-bit instructions, 50 opcodes, and 3 instruction format. And if you are in my lab, you will have a more detailed view of these 3 instruction formats later. And today, we are going to talk about how to support function calls in MIPS instruction set architecture. And we are also introduce you with some other instruction set architecture, well, namely the x86 instruction set architecture. And we are going to talk about the performance. So previously, we talked about a subset of MIPS instructions that I think that will be really useful for CSE141. And most of the examples later on you will see are mainly just into this small set of MIPS instructions. And here is the usage, the meaning of these instructions. And I hope you do spend time looking over it. And in a previous lecture, we used like every of this, we use quite a few in these 4 type categories of instructions. And today we are going to talk about the remaining 2, which is the jump instruction that would help us to support function calls. And the feature of jump and link instruction is that it will store the current PC plus 4, meaning that if we are done with the function call, where's the next function? Okay, we are going to talk about, we are going to use and set the PC to where you are going to jump to, and jump and return just set the PC to the return address that you are willing to go to. Okay, Sujan, do you have question? Question?
Yes, I'm just wondering, like, how is that 25 in JAL?
Okay, so you have to read the textbook. So the thing is that for jump and link, how they encode the instruction is that they encode so saying that you have a PC and we skip the last 2 bits. So it means that if you skip the last 2 bits, so you divide it by your PC by 4. So when you want to make it the PC, you have to multiply it by 4. Are you okay with that?
Yes. Thank you.
Yeah. Okay. All right. So that's the MIPS instruction set architecture, and we have talked about so for this too, right? So that's thinking about like what do we have to do in function calls. So this is a typical C code with function calls, and to do a function call, you need to pass the arguments, and then we change the PC and the control to the callee function, and the arguments and parameters will be visible by the function, but you know, every function has more things that we need. So we need local variables too. And then after we finish, we need to return a value and transfer the control back to the memory. And with the jump and link and jump and return instruction, we are able to transfer the control, but we are not able to pass the parameters and local variables. So this is what we do. So to pass arguments, we have the convention between MIPS instruction set architecture and the programmer or the compiler saying that if you want to pass arguments, you have to put your first 4 arguments in A0 to A3. So this is the convention. You can definitely not following it, but the consequences, you have to bear the risk. So that's what the convention is about. Like everybody should use them in this way. It's not enforced, but you should do this. Like right now, wearing a mask in public is a convention, but nobody would actually like put you in jail if you don't wear it. But it's a publicly, but you have to bear the consequences. Is that somebody would get infected or yourself will get infected. So the same thing here is that there is no strong enforcement saying that you have to do this, but this is a convention that everybody should do. So passing arguments through this 4 registers, but sometimes you will say, well, what if I have more registers than that? Then what we can do is that you have to have them going into the memory stack. You have to have them going into the memory stack. So so that's the convention. And if you want to invoke the function, as we said, jump and link, and the label is the location of the target function, and store the PC adding by 4. And why we need to add it by 4, as I mentioned before, is just because if you don't do it, then it turns out that you will keep going back to jump and link, and you keep calling the function, and you can never go back. And return value, again, this is the convention. You should put it in V0 and return to caller, jump and return. So this is how we achieve function calls basically. And okay, so to give you an example about function call, let's try to use a program that if I'm the programmer, I would never write this kind of program to solve this problem. So this problem is sum of natural numbers, and this program is very simple, and we assume we have a well-behaved user. They can read English, they understand. Enter an integer greater than 0 would definitely give the program an integer greater than 0. So there's no error checking in the sum function. There's no and we just assume this is the program that we are going to dealing with to simplify the example. So if we want to implement this function through the practice we have in the last lecture, it's probably not too difficult for you to compose code like what we've shown in the right-hand side. Is that first of all, that's similar to what I did in the last lecture, is that we just minus the n by 1 because we can still compare if n is 1 or not by after subtracting 1. And the good thing is that if you subtract the n by 1 first, you can actually just compare it directly with branch equal with 0. So in this way you can save an instruction to add 1 to your A0 in this way, right? And the thing is that if you are having an n that is equal to 1, you are going to return 1. So we put a 1 in a return value first, and we may not use it later, right? But if in this way, but if we are using it later, when we figure out it's exactly 0, we go to the return, and the v0 is already 1. So that's the code, and this is the optimization that a compiler might do. And if not equal to 0, then what we will do is to move to the next instruction called jump and link, and the jump and link instruction will go to the sum function. Again, this is called recursive code. If you already learned like CSE 8A, it shouldn't be too difficult for you to understand. And because we are already -1 in A0, so when we call this sum, the A0 still have the argument that we really want to pass to the recursive call. And when we are done with the function code, we will return here, and the v0 in the sum function will give us the result of sum n minus 1. So in this way, we can add it to the original n minus 1, and then add 1 more here. We will get the desired result again. So that's the function itself. And on the caller side, the main function would look like this. We would do a jump and link here to move to the sum function, and we are done. There are some other system call which essentially just represent the printf function here. So the main function is very simple in this way. So right now, it has been a while since we started the lecture. I know you guys want to have some different flavor of the class. So why don't you go through this question and throw me an answer within 90 seconds and let me know what do you guys think. Let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now I'm going to share the voting result with you guys. And it looks like B is a popular answer. However, even with the popular answer, I only see 31% of you think it's correct. But for other answers, everyone has his own advocator. So this is what I'm going to do. So I'm going to try the breakout room function again. And as you can tell, this time I already put Paul was like some of the text from the question in there, and hopefully this time the breakout would work. So let's start. All right, so it looks like a majority of you are done with your vote. So why don't we have someone who is okay to tell us, like, what do you think regarding the answer of the question? And please raise your hand. That would help us to clarify, like like your misconcept. So can I have someone raise your hand? Okay, so I have Dan Ling.
Yeah, so what I think is that when it jumped register to RA and that part, like, I think the program cannot return to the column.
Okay, so the program cannot return. And yes. Why?
I think it's because like from my previous understanding about ARM, we have to push and pop like the registers each time when we do the recursive call. And I'm not sure if this is the case as well in MIPS, yeah.
Okay, so the thing is that you say, well, but why do you have to push and pop in ARM?
Because each time when we call to the next call, we have to preserve the link in order to in order to find where the original address is, and yeah, that's
why do you have to do this?
Because each time
what if you don't do it?
Then I'm not getting back to the original position, original address where I called.
But why you cannot get it to the original position if you don't push it?
Because the register is gotta be overwrite each time when I.
Okay, so it's going to be overwritten, right? And if you don't explicitly store it in somewhere like a stack or something, you are not going to reserve it, right?
Right.
So, okay, so fifth doesn't work. How about others?
I'm not sure the others. This is the only thing I put in. So.
Okay, you think fifth is correct? Okay.
Yes.
Okay, so other thoughts? Some of you? Some of you, like, raise your hand. Okay, so if not, let me go through this example real quick, and you will figure out that there are more things than just that one thing isn't working here. So first of all, right? So let's look at this, right? So we have those pieces of a code, and now this is the registers we have, and that's execute, right? Say we have an input like 2, and here's the program counter, and we try to, and this program counter will help us to set the 2 as the argument for the initial call of the sum. And then what if I when I move to jump and link, right? Remember what the jump link and link would do is that we will save the return address to be PC, the current PC plus 4, which is the address of PC1. And so you can see the return address right now is PC1. Okay, and later on, we will move to the sum as our current PC. So now you see the sum function is called, and our program counter is set to the beginning instruction of the sum. And at this point, this is still the register count 10. And right now, the first instruction asks us to make the number subtract 1 from A0. So you will see on the right-hand side, the register value of A0 is now just 1. And then keep going. This instruction is trying to add 0 to 1. So you can imagine V0 is right now 1. And now let's move to the next. The branch equal instruction. It's trying to compare if A0 is 0 or not. And as you can see, the current value in A0 is 1. So we are not going to return. Instead, we are going to the next instruction, which is the jump and link. And the jump and link instruction saying that you should go to sum again. Okay, but before that, we have to store the return address first. And turns out the return address would be the address after jump and link, right? So we are going to overwrite it, right? So then, so this address is right now something else, right? So and then, well, so let's say it's like a sum plus 20, because for the sum, well, the 20 here means like 5 instructions later, right? So sum plus 20, that's the return address. And now let's move to the sum instruction. And the sum instruction again says that you should subtract the value of A0 by 1. So A0 right now becomes 0. And then you move to the next instruction is that you should set your V0 to 1, which we are fine with that. And now let's move to branch equal. And now your branch instruction, the branch instruction says that, well, if it's equal to 0, then let's go to return. And this time, A0 is indeed 0, right? So is indeed 0. So so we are going to return. And when we return, we are going to jump and return to the return address, which is sum plus 20. So we get back here. And then when we try to add, we are adding V0, A0, and put it back to V0, A0, to V0, right? V0 is currently 1, A0 is currently 0. And so we are going to get a result of 1. And keep going, we are adding 0 by V0 by 1, so we are getting 2, right? And then when we jump and return, okay, first of all, before, are we getting the right return value? Are we getting the right return value, right? For this sum of natural number, if we input 2, we know we are calculating 1 plus 2, right? If you ask an elementary school student, they will tell you, no, this program is wrong. This program is even stupider than me, right? So the answer is definitely not right, right? So first of all, the answer is not right. And second, when we want to return, because the return address is right now sum plus 20, so you cannot get back to the original function. So it doesn't even print. It doesn't even print, right? So here's the thing. If you review this, first of all, well, the program can reach the callee, that's true, and cannot pass argument correctly. That thing, well, we have the A0, so that's true, right? And that's not true, right? We can pass the argument correctly, and the program cannot maintain local variables correctly during the expected scope. That is true, because thinking about that, right? Like originally we have an n that the n in a caller function. However, because you reuse A0, so when we get back, this n is overwritten, and that's why your return value is not correct, right? So it's the return value is not correct. It's because we cannot maintain the local variables correctly, right? So the third one is true. And the fourth one you already know, because you cannot maintain return local variables correctly. So the return value is not going to be correct either, right? And finally, what Danling has identified, the program cannot return to its caller. So actually three of them will not work for this program, which is the answer. Even after discussion, only 8% of you chose. So I do encourage you guys to spend more time looking into the instruction set architecture design later. And I know a lot of you learned CSE 30 before, but you know, different instruction set architecture, they have different concepts, and make sure that you spend time doing that. And the good thing about that is that if you know the instruction set architecture better, it's not helping that much in a class. However, it does help you in a lab. And if you want to make sure that your lab, your processor is functioning correctly, please spend time looking at that. Please spend time looking at that, right? Okay, so the answer here is 3. Three of the statements here are incorrect. All right, so now let's look at the solution. So the solution is that, well, as some of you already identified that previously in ARM or whatever, x86, you have the stack. And stack is essentially backup by memory. And in MIPS instruction set architecture, because we want to simplify the instruction set architecture design, so we are manipulating this memory stack just by ourselves. So we need to add instructions to maintain the stack. So here's what we are going to do. So in addition to register, we use the memory to preserve those local variables and arguments. So here is about the same, but when we call the function, before we call the function, we have to store things in the stack first. And here's the convention. So we move the stack pointer, which is pointed by the stack pointer register called SP. And we minus it by 8 here is because we are going to store 2 variables, the argument A0 and the return address return address of the caller into the stack as well, because we want to store 2, and each of them is 32-bit wide. It's 4-byte long, so it's minus by 4. It's minus by 4 times 2, minus by 8. And we store, we have this 2 store instructions to help us put them in the memory stack. And then we still execute the instruction as what we want to use. And then when we call the function again, this part is essentially the same as the previous iteration. But right now, when we jump in there, well, because this instruction also help us to preserve those arguments and the return address again. So you can see we deduct we move the stack lower, and then we put the local variable and the return address again in the memory. And now, like if we keep going, okay, here it's still the same. However, when we jump and return, well, we return before we return because we store values in the stack. So we have to load the stuff from the stack first. So we have to additionally put this 3 lines of instruction in front before the jump and return. So we load the 1 from the stack to the A0 register. We load the sum plus 20 from the register, and then jump and return, right? So that's how we get back to the previous caller, and we keep going. Here, because we already restored the original value of A0 from the caller, so instead of previously we get the V0 as 1, it's right now 2. And added the 2 by 1, we are going to get 3. Then we get the right answer. We get the right answer. And for this jump and return, we add 3 lines of code here. It will help us to restore the A0, restore the return address. So that's how you get the PC1 back. And when you are jump and return, you can go back to PC1. So that's how you manipulate memory stack in MIPS. So the thing is that in MIPS, you have to explicitly put instruction to maintain your memory stack. But however, it's not too difficult. You just need to make sure that you maintain the stack pointer correctly. You have to calculate how many local variables that will be used in this function, and how if you want to preserve the return address. So that's about it. So with this, you can see every time when you do a function call, there is going to be quite a lot overhead than you can imagine. For example, if you just do the regular function call, you don't need these instructions that we are putting in red or green. So here I'm going to show you something. So function call has a huge amount of overhead, right? And sometimes you will feel like, yeah, if I don't use function, my code is ugly. So here is the remedy of it. In C programming language, there's a keyword called inlining. It would help inline to help us embed the callee code into the code site. So in this way, you don't need to store, you don't need to use the stack because there's no function code involved. So let's see a demo with it. So let me show you this sample program I have. This sample program, I believe, okay, I think I want to have this sample program called popcount_no_up. And we will talk about this program later, but don't be panicked. Here's the program, and there's a random number generator. And some of you say it's a beautiful code, but I will tell you this is the most efficient code of solving the problem. And okay, I have a program that would do the pop count for this many times, because the reason why I want to do this many times, because if you just call it once, the time is really short and it's really hard to tell the function called overhead. And I also have another function called pop count inline. Okay, so for the pop count inline, the only difference is that before this function name, I put an inline keyword here. So right now, well, let's compile them again. and let's run the original version of pop count. So without function inlining, this pop count code would take about 5.5 seconds to execute. However, if we can do an inlining, oops, it's how much? Okay, it's slightly more now, right? It's really? Okay, but what if I don't inline? Okay, so looks like the inlining doesn't work for this example very well, but another thing, but usually you would do function inlining to save the overhead. Okay, so that's one thing that you can probably try out later. But right now, I'm going to talk about another instruction set architecture, and that we are going to conclude the instruction set architecture discussion for this class. So another instruction set architecture I want to introduce in the class is called S86. So this is the abstraction of S86. The modern S86. Why am I saying the modern S86? Because for modern S86, we support 64-bit architecture. So which means that the basic word size is going to be 64-bit. So the register, and when we say like a 64-bit architecture, it means your register is 64-bit wide. It doesn't mean that your integer is 64-bit. So because integer is a data type defined by the language itself. So if you just put int in C programming language, it's still 4-byte wide. So that's the distinction between. So some of you might have the misunderstanding about like it make the integer larger. The answer is no, because integer is just 4-byte, and if you want to use 64-bit integer, you should declare. You should declare something like int 64 in modern C conventions. But here's the abstraction of the x86 architecture. We have a total of 16 general purpose registers, and however, for this general purpose, and they are 65 wide. And there are some specialized registers like this RIP. Well, I don't like the name, but it's actually a register for instruction pointer. It tells you the current program counter. So and because it's a program counter, so you are not supposed to manipulate it, but you can read it. But in MIPS, you cannot directly read the program counter value. So so this is like a specialized register that are not general purpose. And there are flags. Again, the flags, they are not general purpose, and some of the instructions, they will read it implicitly, they will modify implicitly. There are also segment registers. They are not 64-bit wide. So this is the x86 instruction set architecture. And they have quite a lot of instructions. And for the memory part, the current architecture of x86, they support up to 2 to the 64 bytes in their spec. However, most of the processors that you can see only support 2 to the 48. So that's the abstraction of x86 instruction set architecture. And it's the most widely used instruction set architecture for desktop computers, laptop computer, and data center computers. And it's a poorly designed instruction set architecture. It breaks almost every rule of a good instruction set architecture because in MIPS instruction set architecture, every instruction is 4-byte wide. However, for x86, it has variable lengths, and each instruction doesn't have equal amount of work. And because that, so thinking about that, right? Like I'm a nice guy, so that's why your CSE141L is just doing the elegant MIPS instruction set architecture. But if I want to ask you guys to implement an x86 instruction set architecture based processor, I don't think any of you can get a pass for this class. So because the hardware is really, really complex, because you have to deal with variable lengths of instructions, because the hardware design is hard. So So something that we have to let you guys know is that something popular doesn't mean it's good. So for example, like in your reading quiz or say in your pop-up quiz, some questions, some answers popular doesn't mean it's right. So so that's something you always have to keep in mind. And for this class, we don't expect you to know how to write x86, but you need to be able to see at least like what are they doing and try to get a feeling about like how are they different from others. So here's the highlight that I want you guys to learn at least. And we already talked about the registers. And again, for this register, well, the general purpose registers here, they are not actually that general purpose because there are still like some cases that we will use them as accumulator, as the counter, as the data register, as the stack pointer. And there are spatial index register for segments. And there are the instruction pointer, which I don't like their name. And there are flags that will conditionally set by instructions. So the registers, they are not treated equally in x86 instruction set architecture. And the most fantastic thing, or the most terrible thing about x86 instruction set architecture is that there is a spatial instruction called move. And move is the low store instruction equivalent in x86. And it's a single instruction that can go either direction. So it's one instruction, but with many different formats. So this is the 8 format of move instruction in x86. So as you can tell, if you just want to do this, like you can move a value to a register. So in this way, it's like load immediate, and it's only an arithmetic instruction. It doesn't access memory. You can move a register value to another register value. So this is still arithmetic. However, you can move a memory address, the content of a memory address to a register, as what we will see here. And that's like, this is exactly like the load instruction in MIPS instruction set architecture. And but it's more interesting, right? Because we know we have a lot of array. So they also have this format which allow you to access the memory address of a base address plus the index times 4 to access the array easily by just setting the index, right? But in this way, to calculate the address, you need 3 as an arithmetic to make the memory access happen. And there are even more fancier ones, like you can have an offset to the address that you just calculated. So in this way, you are going to have 4 arithmetic to calculate the effective address. And again, you can do the store. You can do the store on the opposite direction of that. So these are all the usage of move instructions. And there are more instructions about that. So because x86 right now is a 64-bit instruction set architecture, so it requires all the move to start with an address that must be aligned with the multiple of 8. Well, okay, I guess. Okay, so here I think sorry. So I think this statement is wrong. So it doesn't require the starting address to be aligned with the multiple of 8. It requires the starting address of each object be aligned with the size of them. So if you have an integer that you want to load, and the starting address of that integer must be a multiply of 4. If you have a double, the starting address must be the multiply of 8. So that's it. So that's the thing, right? The starting address of each object instances must be aligned with the multiple of the size of itself. So that's the convention in x86 that is using. Okay, so given that, may I ask you to try to to think about. Like, you know, your memory access needs to be aligned. Then if you use sizeof operator in C programming language for this data structure, what's the output? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so from what I learned from you, the most popular answer is 32, but okay, I just want to give you guys a hint. The most popular answer is not correct. So right now, I do want you guys to go into the small group discussion again and see if that discussing with your friends to see if that would help. All right, time is up. Okay, so well, after discussion, the answer is kind of like interesting. Okay, so can some of you tell me what happened during your discussion and why do you change your mind? Like, can some of you? Okay, so Tui, what do you think?
So we had consensus on B28 only because
Why?
there's kind of like a confusion between the size of a double versus the size of a pointer to a double. So at first everyone thought that it's still 8 bytes, but which is why we mostly chose 32, but then we said that all pointers should be 4 bytes, so we deducted by 4, which gives us
Okay, so
28.
let me ask you a question. In a 64-bit architecture with 64-bit memory addresses, how many bytes do you need for a pointer? Like how wide is a memory address?
In a 64-bit,
yeah,
it should be 8. That's why I Googled. That's why I'm confused. Like
right.
it should be 4 or 8.
So what's a pointer?
A pointer is an address for
It is an address, and how wide is an address?
32-bit.
No, you just said in
64-bit. Okay.
Right? So how wide should a pointer be?
It should be 8
Right. Okay.
bytes.
So should it be 28?
No, now that you say that, I guess if
Okay,
there's
let's run
doubles
it.
in there.
Right? So the thing is that, okay, I just wrote a program called
Mhm.
hello.c, right?
Mhm.
Here
Mhm.
is exactly the data structure, and
Mhm.
here is exactly the code, right? I
Mhm.
create just one malloc, right?
Mhm.
And well, I can make it one if you guys want. Okay, and let's make it, and okay, make. Let's make clean, make. Okay, let's run it. What's the answer?
40, because you have to align, since they're doubles, even though int is only 4 bytes, you still have to put it in blocks of blocks of 8.
Right. So you got the answer, right? So the thing is that it has to be, you have to align with the data, right? So like if I just have data and next, right? The data start with some address aligned with 4, but the next must align with an address that start with an 8, right? So turns out if you have this data structure, right? ID start with 0, that's okay. But when we go to homework, it must start with a multiply of 8. So you have to skip the 4. Again, participation start with here is okay, but midterm is 8. Average is going to be 8. So it takes a total of 40 bytes.
Got it.
It takes a total of 40 bytes. Okay, I have some of you raise your hand. Nick, what do you think?
Hi, so just a question. If, let's say you had 2 ints in a row, would
if you have 2 ints in a row, right? That's a good question. And let's see it. If you have 2 ints in a row, right? It's going to be 32.
Okay, because they take the same line?
It takes the same line. Well, because now if you have the participation right after ID, right? The address that participation starts is at 4, right? And 4 is the multiply of 4, right? So you are fine.
Okay.
Yeah, and the thing is that some of you learned about compiler optimization. So some of you might be asking, like, if I did compiler optimization, does that help? The answer is no, because compiler optimization won't rearrange those data like this for you, right? So how come it never go back to my slides? What the heck? Wait. Okay, give me a second. Wait, why am I not seeing my slide here? Why am I not seeing my slide here? Okay, here we go. Okay, so the thing is that if you don't rearrange this thing manually, compiler optimization is not going to help you. It's not going to help you. All right. So that's why being a good programmer, you have to know how your instruction set architecture would do with your would do with your code. And the truth is that because we don't support unaligned memory access, so compiler will never do this optimization for quite a lot of reasons. So the main reason is because a struct must be shared by many libraries. So you cannot change the contract that you have to other libraries, and other libraries may apply different optimizations. So it doesn't work out in compiler to optimize it. So the truth is that you think, well, being a programmer, I have a powerful compiler. The compiler can help me deal with that. The answer is no. You have to be carefully assigning your struct, the order of elements in your struct to save your memory usage. So that's one thing that probably a lot of you never learned before. So that's why you didn't get it right. But hopefully this time you understand, wow, being a programmer, I can be really a big part of optimizing a program instead of relying on a compiler. And this is an example that the compiler won't optimize. Okay, Twee, other questions?
Hello? Sorry, yeah, just in terms of what you just said. So the order of the member fields of a struct does matter in terms of x86, but it doesn't matter in ARM. Or
it matters in ARM as well.
Oh, okay. So
yeah,
there's no optimization.
So it is generally true everywhere.
Okay.
As long as the instruction set architecture is better at aligned memory address.
Okay, thank you so much.
Okay. All right, so some of you, should I worry about this in normal day-to-day code? Does it matter? Okay, saying that, well, you know, how many of you have Chrome, right? Raise your hand. Like I know a lot of you have Chrome, right? So the Chrome is very, well, you can put your hand down. Thanks. I know this function works now. So the Chrome is a very memory, is a memory monster, right? And if you, even though you have like 16 gigabyte of memory, it's easily, if you have more than 20 tabs, your whole computer system is going to be really slow. And in many cases, if you want to design saying, and if you use this kind of like memory, like nothing, then it turns out that you are going to write very inefficient code, especially if you are designing software for place with limited memory. For example, mobile phone, right? So you definitely have to care about this. All right. So so that's one example that I will give you. And okay, so for x86, there are also arithmetic instructions. And as you can see, it's even more complicated that an arithmetic instructions, they can access memory as the argument, right? So but for MIPS, remember, only the load store instruction can access memory. So that's a totally different story, right? Branch instruction, they have the compare, they have the jump, and that part is similar. And well, in your homework, I want you, well, I said I don't expect you to write x86 assembly, but I still want to see what it looks like. So I would like you to generate a binary. I would like you to generate a C code, generate the assembly code from your C code. And it's very easy, like what I put here, right? You just use GCC-S, it would give you the code. And what if we do this? So previously I would, so let's see, I have a program called hello.c, right? Like GCC dash s hello.c, right? And now, if you look at that, you will see hello.s. Wow, so that's the x86 assembly code. And well, some of you are thinking about, well, if I cannot really read this, what are they doing? Yeah, I know, I don't even know what are they doing. So a good thing about that is that in GCC compiler, you can use GCC-S-G. The G would give you debugging message. So it would tell you like, information like this, like, okay, here I'm calling malloc. Here is hello.c line 20. Here is line hello.c line 29. Here is hello.c line 31. So you will at least know what the code is doing to help you figure out the function of this your given code. Right, so that's a C2 assembly. And as I said, sometimes optimization does help, sometimes optimization doesn't help, right? And let me give you a positive case how optimization helps. So let's say I have a program called sum here, right? And it does this, and in my make file, I already compiled 2 versions of it, and one is optimization without optimization is -0. And in fact, usually if you don't, well, not this. Usually if you don't put 0, it's by default not optimizing your code. So, but if you put -03, it will optimize your code. So let me compile these 2 versions real quick. And if I do sum, it will take, the normal sum would take about like 1.4 seconds. But if I run the optimized version, it's less than 1 second, right? So in this way, you can see like, okay, if oh, how come? I just hate. Okay, here we go. So in this way, you will see like, you will see that the compiler optimization can help you in some cases. Like, okay, today if I have a boss, he said that, okay, I want you to optimize the code by 30%. Then if you have no idea how to do it, at least try to turn on your compilation flag. That will probably give you a day off in this sense, right? And just don't tell your boss about the secret, just saying that, well, I try to figure out the design space of this program. I apply all I learned in computer architecture to make this program fast, and it turns out that I achieved this 30% improvement in my code, right? So that's the power of compiler optimization. But as I said, there are also cases like this one that we just talked about. Compiler won't do anything for you because it just can't do it, right? So hopefully this stuff would help you. And well, and if you if you want to do the summation code from C to assembly, x86 assembly, here is the equivalent translation. And as you can see, like this has fewer static instructions inside. So right now, a question, the last question I want to have you for x86 instruction set architecture is reading these 5 statements and say, tell me like how many of them is or are generally correct. All right, so I saw most of you voted. So the answer, the most popular answer right now is C, but I still want you guys to discuss with each other because some of you think it's C. Well, most of the time, right? Like as you can see from this shared result, it's like normal distribution. People just like C is, people just think like C is the, because it's in the middle, so it should be the right answer. But the answer is that it may not be right. And sometimes I think there are 3 correct, but maybe your 3 is not the same as my 3. So what it tells us is that I just want you guys to discuss with each other. And whenever you are discussing, try to vote if possible, and so that I know that you guys are done. Okay, let's wrap up in 15 seconds. 5, 5, 5, 4, 3, 2, 1. Time is up. Okay, so let me see what you guys think. So from what I saw here, well, C is still a popular answer, but can I have some of you like explaining like what do you think? And it doesn't matter if it's correct or not. And actually, in fact, I want you guys to be incorrect so that you will have better memory later on. So just raise your hand, and if you don't raise your hand, I really don't want to do this, but if you don't raise your hand, I will randomly select some people. So it's better that some of you raise your hand to keep the class up and rolling. Okay, Tui, you are the star. What do you think?
So I know 3 are correct for sure.
3. Okay, what are the 3 you think?
So x86 provides more instructions than MIPS, and x86 may access memory for 3 times, and
what are the 3 times you think you have in mind?
It's one of the example that you provided where it basically it accesses an index of an array using its base address, something like that. Or maybe there
are
move
but it's just register, right? It's just register.
Maybe there are move instructions that are able to access memory 3 times. I'm
Okay.
suspecting. And
Maybe, but you are not sure, right?
yeah, and
Okay.
then the other one is that x86 instruction may be longer than MIPS instruction.
Maybe longer than MIPS instruction.
Although I am iffy about number 4 because that could be true also.
Okay, other thoughts? Other thoughts? Other people, what do you think? What do you think? What do you guys think? Okay, so, well, so first of all, it provides more instructions and MIPS. That is true. It usually needs more instruction to express the same program. That's not true, right? We just compile the sum.c, but an x86 instruction may access memory first 3 times, but I want to have a clarification on this. So the move instruction can only access data memory for 2 times. However, don't forget your instruction is also in memory. So instruction itself, you have to get it from memory. So that would be the third, that would be the one that you guys may be forgetting. So first of all, every instruction would have a memory access, but it's instruction memory access and 2 for data access for the move instruction. And an x86 may be shorter than a MIPS instruction. That is true. So I can give you an example here. So saying like, okay, so, okay, like this move instruction, right? Like we have a move instruction here, right? All you need to do is put 6 there, right? So, so this instruction could be really simple, right? And the thing is like, so this instruction can be really, really simple if you just put a 6 in there, right? And for x86 instruction, this instruction only have 1 register, one immediate value, 1 register, which is even shorter than the equivalent ones in MIPS instruction set architecture. And the shortest x86 instruction is actually just 1 byte. It's just actually just 1 byte. But why? Because that 1 byte instruction is just like a pop instruction and a push instruction. When you push and pop, you don't even need to register. So that instruction can be just 1 byte. So x86 is a very annoying instruction set architecture in a way that, well, the instruction can be shorter or longer, right? So 4 of them here, they are correct. So you know like how terrible x86 is, right? So the shortest x86 instruction could be 1 byte. And the longest x86 instruction could be 17 bytes. And for MIPS, everything is just 4 bytes. And the code size, and as I said yesterday about the code size referred to the number of static instructions in MIPS because you need more instructions, so it's generally larger. The number of registers, MIPS has more, x86 has fewer. And for addressing mode, MIPS only have rec plus offset, but for x86, there are tons of them. And the hardware, as you can tell, MIPS is simple, x86 is more complex. So, and because it's complex, so in most of the popular instruction set architecture, they are called reduced instruction set architecture computers. And this reduce is referring to x86, which belongs to another category called CISC, complex instruction set computers. So these are the modern processor architecture, and including MIPS. Most other instruction set architecture that are currently alive belongs to reduced instruction set computer, and every instruction just performs simple tasks. And the concept of x86 is to provide many powerful complex instructions. And in modern x86 processor, you have to support 1,500 instructions. So here's I think this slide, right now we conclude all the discussions on the the instruction set architecture. And before you leave the lecture, there are several things I want to let you know. So first of all, assignment 1 is up due next Monday. Before the lecture, check the website for the template, submit the PDF through Canvas. And the discussion session will be mainly about how you can address these questions from your assignment. The next reading quiz will be due next Tuesday. It will be a while ago and it's already up. So if you want to, if you finish your assignment and left early, it doesn't hurt to spend time going through those reading quizzes and read those resources that we have and use them wisely. Other than that, I will see you later today for a lecture or tomorrow for the lecture.